Hi everybody. Now that we know how to determine if something is ionic or covalent, we can start learning how to draw and represent these molecules. In order to do that, we're going to use something called Lewis dot structures or Lewis dot symbols. So they're a way to represent what's happening with all of the valence electrons and what they're doing inside of these bonds. So in order to do that, first we want to write the atom. And then for every one of the valence electrons, you would draw a dot around that atom. You'll notice that for whatever group that element is in, it'll have the same number of valence electrons. So silicon and carbon, for example, those are in group 4, so those would have 4 valence electrons. Chlorine and all the halogens are in group 7, so those would all have 7 valence electrons around them. You'll also notice that you put 1 on each side of the atom, so you can imagine a square around each atom. For each side of the square, you put in 1 dot until you have 1 in each, and then you start pairing them up. So we can use Lewis dot structures to illustrate how electrons are transferred during the formation of an ionic bond. So we'll use magnesium fluoride as an example. Fluorine has 7 valence electrons each, and there's 2 of them. Then magnesium has 2 valence electrons in that. So those 2 valence electrons in magnesium can be transferred to the fluorine. 1 would go to each one of the fluorines. And you'll notice that after that, fluorine now has 8 electrons around it, and we call that an octet. Magnesium would also have an octet around it as well, but it would not be they would not be valence electrons, they would be the core electrons. So after we see that transfer of the electron, like I said, we see the octet around the fluorine. Oftentimes, if something does have an octet, we don't even need to write the 8 dots around it, so we would just write F minus like we see on the bottom. And that's oftentimes why we just write Mg2 plus or F minus without actually representing the dots around it. It's just sort of assumed that we know they're all there if it is F minus. We don't use Lewis dot structures too often with ionic compounds, but that is an option that is available to us. We use these Lewis structures much more frequently when we're talking about covalent compounds. So let's start using hydrogen as our first example. So each hydrogen has 1 electron or 1 valence electron in it. And as we know that H2 is a covalently bound molecule, so those 2 are going to share the 2 electrons. You're not going to see transfer of one to the other. So in order to represent the sharing of the electrons, we would have 2 dots in between the 2 atoms that are sharing the electrons. So you can imagine a circle around each atom and the electrons that it's sharing. So now hydrogen, of course, is in the 1s energy level. All the electrons are in the 1s energy level, which can hold 2 electrons. So you can imagine that the 1s electron in each hydrogen now has 2 electrons in it. So that has a full subshell. Even though it doesn't have an octet, that whole n equals 1 energy level is full. We can also represent a pair of shared electrons with just a single straight line, and that's what you'll see more commonly used once you learn how to start drawing these structures. Here's another example, this time with fluorine. So you'll notice fluorine has 7 valence electrons with 1 that's alone and by itself, or what we call unpaired. So it's those 2 unpaired electrons that end up getting shared with each other. So you can see that after they're shared, if you imagine 8 electrons around each fluorine, if you were to draw a circle around each fluorine, including the 2 that are being shared, you'll notice that each fluorine has 8 electrons around it, or it has an octet around it. So recall that fluorine is in the n equals 2 level, or energy level. So that has 1s and 3 p subshells in that energy level. So that an n equals 2 can hold a total number of 8 electrons. So that's why we get that number of 8, or an octet. And as before, we can represent those shared bonds as a straight line. That is a much easier way to do it. And also, as you start to draw these more often, you'll oftentimes you will leave the dots off around the outside of the fluorines because it is, again, assumed that they are there. But for now, I would keep them in while you're practicing doing this. Here's another example, this time with HF. So I already have the two bonded together. You'll notice this time hydrogen still has the 2 that's being shared, but fluorine is also has 8 around it. So we can also represent that with the bond like we see in the bottom left. So now a little more terminology that we'll introduce. You'll have the pairs of electrons that are around the fluorine. We label them as lone pairs. So each pair acts almost like an individual unit. Then the part that is bound, that's holding the hydrogen and fluorine together, that's what we call the bonding pair. All right, so what happens if there are still unpaired electrons? So if we look at oxygen, if we take 2 of the electrons that are unpaired, because oxygen has 6 valence electrons, and we pair one of those up, you'll notice that there's still an unpaired electron that's on the top of each oxygen. And the same is also true for nitrogen. So nitrogen has 5 valence electrons. If you share one set of electrons, you'll see 1 electron on the top and bottom of nitrogen that's still unpaired. So when that happens, you never want to leave an electron alone like that. You always want to have an electron in a pair if it's possible. So in the case of oxygen, those other 2 electrons that were by themselves, they also get shared. So for something like O2, you'll see 4 total electrons being shared between the 2. And if you share all 4 of those electrons, you'll end up with an octet around each oxygen. If you don't share both of those free electrons or unpaired electrons, you'd only have 7 electrons around each oxygen, and that would not give oxygen its octet. Now with nitrogen, so both of those unpaired electrons in each will be shared, so you have a total of 6 electrons that are shared between the 2. In that case, it gives each nitrogen an octet. We can also, again, represent these with straight lines, which represent the bonds between them. And you'll notice that oxygen has 2 bonds being shared, whereas nitrogen has 3 bonds being shared. So we would say that nitrogen has a triple bond and oxygen has a double bond. In the previous examples, when we looked at fluorine and hydrogen, those all had single bonds. All right, so now let's look at some molecules that have more than 2 atoms in it. We'll start with CH4 and CO2 because those are both pretty common molecules. So if we take 4 hydrogens, each with 1 lone pair, and then carbon, which has hydrogens with 1 valence electron, then carbon, which has 4 valence electrons. And if we pair each hydrogen up, the 1 electron in the hydrogen with the 1 electron in carbon, we'll see that we can make 4 carbon-hydrogen bonds. So we have a carbon with 4 hydrogens surrounding it. Now if we look at CO2, of course, again, we have oxygen, which has 2 unpaired electrons, and carbon with 4 unpaired electrons. So we'll start by pairing 1 up for each side. Then you'll notice that there's still 2 unpaired electrons in carbon, plus 1 unpaired electron in each oxygen. So we can match 1 in carbon with 1 in oxygen for each side. Then you'll see that there's 2 bonds connecting carbon with oxygen. And we still have those 2 lone pairs on the outside of each oxygen. So a couple trends that you'll start to see as we begin to draw more and more of these molecules. You can always tell, or usually you can tell how many bonds each atom will have by seeing what family that atom is in. For example, carbon is in row 4, which had 4. So carbon, of course, has 4 valence electrons, and all 4 of those are unpaired when you look at the Lewis symbol for the carbon atom. And carbon, you'll find, likes to have 4 bonds. And that can be a combination of 4 single bonds, 1 double bond, and 2 single bonds. It can be 2 double bonds, or it can be a triple and a single bond. So there's a lot of combinations you can have, but in the end, carbon typically has a total of 4 bonds to it. So nitrogen usually has, nitrogen, the valence symbol for nitrogen has 3 unpaired electrons. So you'll notice that nitrogen usually has 3 bonds to it. And that can be 3 single bonds, a double and a single, or it can be 1 triple bond to it. Oxygen has 2 unpaired electrons, so typically you'll see oxygen with 2 single bonds or 1 double bond to it. In the halogen family, which starts with fluorine, they have 7 valence electrons with 1 unpaired electron. So usually the halogens only have 1 single bond to it. If we go in the other direction, you'll see the same trends. So the boron family likes to have 3 bonds to it. The beryllium family typically makes ionic compounds, but sometimes you'll see 2 bonds to beryllium. So when we're drawing molecules in more than 2 atoms, that's a general rule. We always put the least electronegative atom in the center. And of course, hydrogen can never be in the center of an atom because hydrogen can only have 2 electrons around it at most. So if you add up the total number of valence electrons in your structure, or if you add up the total number of valence electrons in each atom that's in the molecule, that number has to equal the total number of electrons you put into the structure. And also, if you draw in the Lewis structure for an ion, you need to add or subtract the appropriate number of electrons from your structure. So if you take something like fluorine, which has 7 valence electrons, and you compare that with the fluorine ion, you'd have to add 1 electron because the negative, if it's fluorine -1, that means you have 1 extra electron. So let's try PCl3. We're going to do this step by step. So if you're not sure where to start, these are a simple set of rules you can usually follow and draw these structures for yourself. So we start off by figuring or adding up the total number of electrons that we need to have in our structure. So phosphorus is in row 5, so that has 5 valence electrons. Chlorine is in row 7, so each of those chlorines will have 7 electrons. So the total number will be 26 electrons that we need in our structure. So now when we start drawing, we want to put the least electronegative atom in the center and then attach each of those atoms with a single bond. So if we're supposed to have 26 electrons, right there we just used up 6, so that means we still need 20 more electrons. There's still 20 more electrons that have to go in that structure. So now after you do that, you put lone pairs around each periphery atom to give each atom an octet. So here I put 2, periphery means outside, of course, so I put 2 or 3 lone pairs around each chlorine. So now each chlorine has an octet. So in this step I added 18 more electrons, and that leaves you with two electrons that you still need in our structure. And the last step is to put any remaining electrons on the central atom. And that would be our final structure for PCl3. And here we have a really good structure, and everything has an octet. If you get to this step and you don't have any electrons left, so let's say we don't have an octet around the central atom, but we already used up all the available electrons, this is when we have to start considering double or triple bonds to the central atom. So let's look at COCl2. I already skipped to step 3, so I skipped the first 2 steps. We needed a total of 24 electrons in this molecule. I put carbon in the center, then I have 2 chlorines and 2 oxygens on the outside, and then I filled up the outside atoms with an octet. So I'm already out of atoms, but yet carbon doesn't have an octet around it. So I mentioned before that in this case we're going to have to take 2 of the electrons that are in lone pairs and make those make a multiple bond, or have a double or triple bond to the central atom. I mentioned before that oxygen likes to have 2 bonds, so that is usually a good place to start. So here it would be the final structure. I took 2 of those electrons that were in the lone pair on oxygen and made it a double bond on the carbon. So now we can see everything has an octet. Carbon has 4 bonds to it, and carbon likes having 4 bonds. Both of the halogens have 1 bond, and they like having 1 bond each. And then oxygen likes having 2 bonds, so now there's 2 bonds to the carbon. There are a few exceptions to the octet rules. Some atoms can have more or less than 8 electrons around it. Anything in the boron family, so like boron or aluminum, are the most common. those can have 6 valence electrons around it, and they're pretty happy. And anything that's in row 3 or down can have occasionally more than 8. All right, so if we look at boron, boron has 3 valence electrons around it, so you can fit three bonds to it pretty easily. And boron is not a very electronegative atom, so it's more electropositive. So it's actually somewhat happy being electron deficient like it is now. It's sort of happy not having a full octet, and there's nothing wrong with that. So BCl3 and BH3 are 2 that we see very commonly. Also, aluminum compounds, you'll see the same thing. So something like aluminum chloride or aluminum hydride, like AlH3. So whenever we're in row 3 or below, if you recall, whenever n equals 3, we can have s, p, and d orbitals. So when we are drawing Lewis structures for these metals, we're particularly working with nonmetals now, even though some of the transition metals can still do this. If we look at just the row 3 ones, but this also applies anything at row 4 and down. If you take a nonmetal in row 3, such as sulfur, all of those valence electrons are in the 3s and 3p orbitals. But there are 3d orbitals in that molecule, but they're at the time being, they're not being used for anything. But those empty orbitals are there, and those are available for bonding. So PCl5 and Cl6 are both good examples. Like here we have PCl5 and SCl6. And I didn't draw all the lone pairs in, but each chlorine would have 3 lone pairs of electrons around it. And you'll notice that phosphorus and sulfur each have more than 8 electrons around it. So phosphorus has 10 electrons currently, and sulfur has 12. And also it's important to keep in mind that most of the time these elements will satisfy your octet rule, but if you're in row 3 or down, it's okay to not have them or over violate it in certain cases.